basically is superposition of waves which are of different frequency now, and then you will see that it gives rise to beats, and then we'll talk about phase and group velocities and dispersion. For beats phenomena, we start with two waves. They are of comparable amplitude or about the same amplitude, but they would have different frequency, and they also would have different wave numbers. So for wave 1, we would have wave number K1 and frequency omega 1. Wave 2, we would have K2 and omega 2. I'm going to assume that it's a medium that's non-dispersive. That means different frequency wave will travel at the same speed. And from the principle of superposition, we will have the linear combination, which is just summing the two waves. Now we factor out the common amplitude, and using trigonometric identity, then cosine of this add to cosine of this, representing the phase here by alpha, and K2x minus omega 2t as beta. We can write in this term and expanding and putting all the values in. So we have this term, add on this term divided by 2, and this term minus this term divided by 2. Group the axis together and the time factor together, the space and the time factor together, and then these two divided by 2 would give you the average frequency, and here too it will give you the average wave number. And the differences would be written as omega 1 minus omega 2, half that, and K1 minus K2 divided by 2. And we can then simplify this equation into Kpx minus omega pt cosine of kgx minus omega gt. You will find later that P would be representing phase, G is denoting group. What we have here as a resultant would be the product of two cosine waves. So how do we visualize that? Okay, here is an example whereby we have that's the resultant of the two waves. This is what you will see. The high frequency component here is what we call the carrier wave. Now it's varying very fast. And then we have another slow varying cosine function here. It will limit that carrier wave's amplitude, and we can also denote it as an envelope wave. And this is of lower frequency. This low frequency wave will serve as an envelope that modulates this high frequency wave in such a way that it will produce beats. Here is an animation of the beat wave. The beat wave is represented by the blue wave, as you can see here, and is created because from two traveling waves with just slightly different frequencies. And these black dots are to help us watch at these two reference plane when these two waves passes, and when they add up, what we get over here. Now, if you note at the peak, you'll find that they all are aligned. And then let's note at the point where it becomes zero. You see wave 1 and wave 2, they are out of phase, out of step. When the two crests, that's the two peaks, align with each other, you get constructive interference, give you the maximum amplitude of the beat wave. When the peak lines up with the trial valley, then they cancel out and you get destructive interference. So drawing them in steel, this is what you see. The difference is very small. So as you can see here, they interfere destructively, you get zero amplitude. They interfere constructively, then you get largest amplitude. So they're modulated by this envelope. Okay, this is redrawn of the carrier wave and the envelope wave, but we have removed the part that has been capped by the envelope wave. It is drawn with respect to time. So you can imagine that you put a marker and the wave travel past the marker with respect to time. So these are the oscillation that I see. Just like in the previous slide, we were watching the blue one. If you stay here, you can see all these waves passing through it. That's what we see here with time moving. Then we find that this envelope actually moves with certain speed. As you can see, the envelope itself is moving with certain speed. But the carrier wave also moves with its own speed, which is called the phase velocity. And the envelope wave will move with a velocity called group velocity. Now, for light wave, we talk about energy delivered. We talk about the irradiance, which is proportional to the wave displacement squared. Therefore, the energy delivered by this sequence of pulses would be traveling at a bit frequency. So if you look at what we have here, the group, the angular frequency, is given by this wave. And if you look at the beats, it is actually beating at a frequency which is 2 times higher than the group frequency. And in that case, you will find that the beat frequency is equal to just the difference between the frequency of the two constituent waves. Now here is plotted with respect to distance, so we sort of freeze it for a moment. And here we have two waves, E1 and E2. E2 is represented by the dashed line. I think there is a mistake here. If the broken line is represented by E2, then this should be lambda 2. And if this full line is representing E1, this should be lambda 1. At the point where they interfere destructively, you're going to get zero amplitude. At the point where they interfere constructively, we get the maximum amplitude. So these are the beats, 1, 2, 3. So beat, beat, beat. And the envelope is actually like that, yeah. We were talking about irradiance, which is the squaring of this envelope. So when you square it, you will get a waveform that looks like this. So here you will get the beats actually. You get maximum irradiance, maximum irradiance, maximum irradiance. So this becomes one beat. That's why the frequency of this will be 2 times that of the envelope wave. Here is an animation to give you an idea of a phase and group velocity. The red dot is following that carrier wave. See, it just follows that wave as it travels through space. The green dot is always at that 0 point. That is going to denote the group velocity. In this case, you will see that the group velocity, the green, is less than the phase velocity. An important interpretation of group velocity is that it represents the velocity at which the energy of the wave, or in this case, the information, is conveyed along a wave. You can actually check out animation in YouTube video given by this link here. And you will see in this case the group velocity is traveling at a higher speed than the phase velocity. Okay, we're going to look into phase and group velocity in a light wave pulse. And we're going to do some math as well. When you have a light pulse, it can be represented by the superposition of many harmonic waves of different frequencies. And this we all know from Fourier analysis. And I do hope you remember that. But in case you do not remember, let's do a little bit of refresher course. This is a Fourier analysis of, we're going to take an example of a square pulse afterwards. When you add harmonic wave of the same frequency, though their amplitude and phase may be different, it would result in a harmonic wave of the same frequency. But if we were to superpose waves of different frequencies, then it will result in a periodic wave, but it will not be a harmonic wave. It will become a n-harmonic wave. By summing different frequency waves, we can synthesize pulses of various shapes. The inverse process, of course, would be to decompose a certain waveform into its harmonic components that will bring us to Fourier analysis. According to theorem of Dirichlet, now if a function is a bounded function and it has a period of t, having finite numbers of maxima or minima or discontinuities in a period, then the Fourier series can be written as in this form, whereby this Fourier series here will then converge to that function, that bounded function, at all points where the function is continuous, and to the average of the right and left limits at each point where the function is discontinuous. So we're going to look at a discontinuous function afterwards. Now, I rewrite the expression, the Fourier series here, which is noted as equation A1, where m is actually an integer, omega is 2 pi f or 2 pi over the period t, am and bm amplitudes of the respective harmonic waves of frequency m omega, whether it's written in cosine or sine terms, and the magnitude of am and bm will then determine how much each of the harmonic wave will contribute to create that pulse. We would like to then find out how do we get this amplitude value. So what we do is, if we were to multiply the series with dt and integrate it over a period t, this cosine and sine term will vanish, because when you integrate over one period, this cosine and sine term will take values distributed between -1 to 1. So when you add them up, they vanish. We will then be able to obtain A0, which will then be equal to 2 times the integration of the series over one period, starting from t0 to t0 plus t, and divided by t here. And if we were to multiply this expression by cos n omega t dt, where n is any integer, and then we integrate over the period t, which is written in this form here, multiply with this, integrate over t, then we will be able to get the expression for amplitude, am here, or we write here denoting as n here. And similarly, if we multiply A1 with sine n omega t dt and integrate over one period, we will be able to get the value for Bn or Bm. If then the Fourier series is specified, all this can be computed. So we would be able to do a complete analysis. So let's try a square wave represented in this form, whereby this square wave will take up the series will take a value of 0 from negative t over 2 to negative t over 4. From negative t over 4 to positive t over 4, it has a value of 1. and from T04 to T02, it has a value of 0. So that's one whole period here. So as we have learned earlier on, A0 then is integrating this over one period, which will be from negative T over 2 to over 2. We have values only between here and here, 1. So we then narrow down the bounded limits here. So from negative T4 to T4, then we will have T04 plus T04, that's T02, cancels with this, and you get it to be 1. For AN, here we multiply by cosine n omega t dt, and we integrate over one period. Integrating this, we know that we only have a value from minus T04 to T04. So this function is 1 when it's from minus T04 to T04. And integrating cos function, you get a sine function divided by n omega. Now omega is 2 pi over t. This will give us t over 2n pi. And here it will give us 2n pi t over the period. So putting these values in the end, you will come to an expression which is 2 over n pi sine n pi over 2. Similarly, for Bn, you can go through this in detail on your own. However, you'll find that cosine of a pi over 2 is 0. So in the end, this Bn term is actually 0. Using these results, we then put it back into this Fourier series. It will converge to A0 over 2, so that is half plus, now this term is 0, so it's no more there, summation of m or n, because just now we were representing n when we were trying to get the expression for the amplitude. And here will be written in this way, and you will know that this term here, when n is odd but it takes 1, 5 or 9, it is positive. When it takes value of 3, 7 or 11, it becomes a negative 1, and it is 0 for every even n. That's why when you sum it up and writing it out in detail, you will get the series to be half plus 2 pi, which is constant. When n is 1, you only left with, so this is 1, you're left with cosine omega t. When n is 3, you will have a negative 1 here, negative cos 3 omega t, and so forth. Now, this square pulse can then be represented by this series. And if we only use 3 terms, you'll find that it will be represented by this one here, which is not so close to it yet. And if you increase the number of terms, now you go to 10 terms, well, it gets more and more like the square pulse. And if you go to 100 terms, then you have a better representation. So from here, you'll note that the fine features of this series, that is at the corners of this square wave, will require waves of smaller lambda or higher frequency components, in other words. Otherwise, you'll miss all these fine features, these sharp corners here. So if the square pulse is narrower in width, like a spike, the contribution from high frequency components would be greater. Let's go back to the original slide. We've done some discussion on representing any shapes using Fourier series representation. What we learned was when a pulse is very narrow, then you will need to represent it using a composition of harmonic waves with a larger range of frequencies. In other words, the duration of a pulse is inversely proportional to the range of frequency of the waves that superpose to form the pulse itself. So delta t is proportional to 1 over delta f, f standing for frequency. Now, in reality, monochromatic light that we ideally think of as single wavelength, which implies that it has an infinite spatial extent and it also exists infinitely. However, it actually has a narrow spread of wavelengths, about its average wavelength. Because of this, when this light propagates through a refractive medium, dispersion will occur because the light component of the different wavelengths, they will travel at different speed. And usually when the medium is absorptive, even if it's weakly absorptive, it must be dispersive. So the interaction of light with an absorptive medium would then affect the speed of the wave. We talk about a train of wave pulses. A train of wave pulses will result when the component harmonic waves superpose, such that the high amplitude pulses will occur at the times and position when you have constructive interference, as you've seen in producing the bits when two close by wavelength interact. And in regions of low amplitude, then that is a result of destructive interference. So if the harmonic components move with different speeds, the position of the net constructive interference would then have a complicated relationship to the speeds of the constituent harmonic waves. And that would give rise to two different velocity, which we call the phase velocity and the group velocity. Now, the phase velocity is a measure of the velocity of the harmonic waves, the constituent waves that make up the signal. And the group velocity would be the velocity at which the positions of the maximal constructive interference propagate. Let's look at it visually, which you have already seen earlier on. This one that's animated. The green dots is the group velocity. The red dot is the phase velocity. You see, the phase velocity is the velocity of the constituent carrier wave, whereas the green dot, which is the group velocity, is the velocity of the envelope wave, when we were looking at interference of two waves of different frequency, but they are close by. Now, any two wavelength components of a light beam, that's the simplest example, taking two components, moving through a dispersive medium, we can represent them using cosine function. We can assume them to have the same amplitude, but they would have a different wave number or propagation constant, and here also different frequency. And then they will produce a wave that we've done this earlier. And then the velocity of this higher frequency wave, this blue phase velocity, and the velocity of the lower frequency envelope, that will give us the group velocity. They can be deduced through the relation given by this. The velocity is related to the frequency and the wavelength, and we can equate it to the angular velocity divided by the wave number or the propagation constant here. Now we're going to derive the relationship between the phase and group velocity. We will consider the superposition of two component harmonic waves, each of them having omega 1 and the other one omega 2, and wave 1 has a wave number k1 and wave 2 k2. So the phase velocity is given by omega p over kp. P here stands for phase, which will then be equal to the sum of this divided by the sum of this. Now they are both about the same, so we can then take an average and represent that using a single symbol here, omega, can be approximated to omega over k. We have used this approximation, and this is almost equals to k. They are very close by frequency and wavelength components. What about the velocity of the envelope wave, which we have named it a group velocity? Now the group velocity is equal to the ratio of omega g over kg. Now omega g is the difference between the angular velocity of the constituent waves, or we can relate that to the frequency. This is also the difference. So that can be approximated to d omega over dk. We have assumed that the differences between the frequencies and the propagation constants to be small. This one, the phase and the group velocity need not be the same. They can be the same, but it need not be the same. Comparing phase velocity and group velocity. If phase velocity is larger than group velocity, then the high frequency waves will appear to move to the right relative to the envelope. Both of them are in motion, which was this case here. You see, the red dot is moving to the right. The green is also moving to the right, but the red is moving to the right of the green. So both of them are in motion. But if the phase velocity is less than the group velocity, then the relative motion would be reversed. So if the phase velocity is equal to the group velocity, they both will move at the same rate. There will be no relative motion between them. We would like to now get a relationship between Vp and Vg. We will start with Vp equals to omega over k, Vg equal to d omega dk. So substituting for omega, which is equal to k Vp, we get this. So then as you differentiate, you have a 1 here, so you're left with Vp plus k dVp dk. Now let's look into non-dispersive medium, which is the case in vacuum. In non-dispersive, it means that the velocity of wave would then be independent on the wavelength, which means that dVp dk will be 0. In other words, we will have Vg equals to Vp, and that will be equal to the speed of light in vacuum. In dispersive medium, Vp can be written as C over N. That's the relation for the refractive index. So N, as you know, is dependent on lambda or K. So then we have N, which is dependent on K, is here. So for dVp dk, then we will have substituting for Vp C over N. So the variable is dN here. So then we will have differentiating with respect to dN here, we will have negative C over N squared dN. So then we have this expression. And then now we incorporate this back into equation 8 here. So we have Vg plus Vp. We substitute this back in here. C over N is equal to Vp. So we can factor that out, leaving behind negative K over N. So then we have this expression. That is Vg in terms of Vp related to that. And we have these terms. Now we have already derived this expression. So now we would like to write in terms of d and d lambda. So the relation of k and lambda is given by this. K equals to 2 pi over lambda. So dk will then be equal to negative 2 pi over lambda squared d lambda. And using this expression here, whereby negative k over n dk, we can write as 2 pi over lambda, which is k, and still remain. dn dk can be written as dn d lambda dk. And d lambda dk is given by this expression here. So that will be equal to negative lambda squared over 2 pi. So substitute that into this one. This becomes positive. 2 pi cancels, one of the lambda cancels, so we're left with positive lambda over n. So therefore, we will have 1 plus lambda over n dn d lambda, as in equation 10. Now, in the regions of normal dispersion, for example, in various types of glasses, as you can see here, They all have different refractive index, and they are dispersive medium. And you will see that the gradient of this variation of irrefractive index with wavelength, the gradient is negative, is less than 0. So for normal dispersions, you will have dn d lambda less than 0. So when dn d lambda is less than 0, which means it's negative, 1 minus something will give you something less than 1. So you will find that Vg would then be less than Vp. Now let's look in the case of a waveform that's made up of harmonic waves with a wide range of frequencies. We will get something like this. This is a snapshot of a waveform that is the sum of 10 equal amplitude harmonic waves, and the frequency spacing about 1/50 of the average frequency of the constituent harmonic waves. Earlier on, when we have just one beat and the next beat, that was for 2 harmonic waves. Now we are doing 10 harmonic waves. You will find that you can actually get narrow pulses. You can see where the amplitude is very large, and then you still have the region of low amplitudes where you still have these beats, but they are very low amplitude. So this high frequency part is the carrier waves, and that will move with phase velocity, but this envelope will move with group velocity. So in other words, the group velocity will determine the speed at which energy is transmitted. It is a direct measurable speed of the waves. Now let's get another expression which we would like to write in terms of dn d omega. This is also the frequency. Now k is equal to omega over c. So dk d omega will just have a constant c here. So d omega dk would then be c. Going back to equation 9, dn dk can be written as dn d omega dk. Now d omega dk, as you know, is c, and k we have substituted with omega over nc. So having that, so c and c cancels, we have omega over n dn d omega that. So we have this simplified expression. Now, in order to simplify further, we're going to make some assumption. We're going to factor out the n, so we have this expression here, and we multiply this by n plus omega dn d omega on the numerator and the denominator. We get n squared minus omega squared dn d omega squared divided by n plus omega dn d omega. And when we multiply them out, you will get c over n plus omega dn over d omega minus c over n plus omega dn d omega also. And you will have this term here, omega squared n squared dn d omega squared. So factor this out, that will leave us with 1 minus this squared term here, which is small, which is very small. So when this is very small, then what we have is we will then be able to approximate that to an expression that looks like this, c over n plus omega dn d omega. So now we have another expression. Now you'll find in some tags, some diagrams, you will see that the reflective index, the dispersion curve, is given relative to omega. And if you look at this, dn d omega in the normal dispersion would then be positive. And at parts where you have a steep drop, these are regions of anomalous dispersion where absorption actually occurs. So in non-absorbing regions or in regions of normal dispersion, now we already know that Vg would be lower than the phase velocity. So dn d omega is positive. If this is positive, this number will be larger, then Vg will be less than c. The diagram of n varies with omega. Now if we flipped it, taking the mirror image, the relationship of lambda to omega is inverse. So then you'll find that at normal dispersion, dn d omega is positive. For dn d lambda, it is negative instead. Now in absorbing regions here, which we call anomalous dispersion, you'll find that Vg is actually larger than Vp because dn d omega is negative and is very steep, or we have dn d lambda positive. So in this case, Vg is larger than C for these wavelengths, this range here, the shaded range. Now these results hold in general for more than two waves with narrow range of frequencies and may be characterized both by the average velocity of individual waves and also the group velocity, which is the velocity of the modulating waveform. As Vg determines the speed that the energy is being transmitted, it is a direct measurable speed of the wave. For example, in amplitude modulation, that's AM wave, the carrier wave modulated to contain the information. So Vg is carrying the information, that's the signal velocity. And another example is for light pulses that are made up of a number of harmonic waves that can extend over a range of frequency. And these are being transmitted through a dispersive medium. So the group velocity will be the velocity of the pulses that results, not the velocity of the individual harmonic waves. In wave mechanics of electron also, it is represented by localized wave packet, which constitute a number of harmonic waves with a range of frequency. And the measured velocity of the electron will be the velocity of the wave packet, and that will be equals to the group velocity. What is wave packet? It is a short burst or an envelope of localized wave action that travels as a unit. Now, in a medium with no dispersion, the wave packet will travel as a whole with no variation in the oscillation. And but then if there is dispersion in a medium with dispersion, then you see the traveling wave packet, the oscillation is actually changing. Can you see the difference between the left and right diagram? Right? In those anomalous dispersion region, we said that the group velocity can exceed C because in terms of d and d omega, this is negative. So this number becomes smaller, so VVG becomes larger. One problem is that in this anomalous region, absorption is very strong. You'll find that d and d omega is only steep when this region is narrow. This is the resonance region. So only a narrow range of frequency would have Vg larger than C. Frequencies outside this range will have Vg smaller than the speed of light. In this case, what we're saying is that, and the problem that we encounter would also be that pulses of light, which are broadband, would then break up into a mass. So what do we mean by that? When the wave propagates in a material, so as long as the pulses hold together as constituent harmonic waves propagate, the group velocity is viable. But in general, these pulses spread. As they spread, they are superposed and they will distort as they propagate because each of the harmonic components travels with different speed. So if this velocity of the component harmonic waves differ by a sufficient amount, the pulses will break apart and no single group velocity can be assigned to the signal. And this is definitely not good for telecommunication systems. Now let's look at this. Let's say we have a train of narrow pulses in telecommunication. Because of dispersion, these short pulses is going to spread as it propagates, and they become long pulses. And you know that in telecommunication, we want this pulse to travel many, many kilometers fiber. So after traveling that, you see each one of these has broadened. And look at the shape, you could hardly make one from the other in the end. In other words, we're going to say is that dispersion will dictate the wavelengths at which telecommunication systems can operate. And it will also require the fiber to be carefully designed to compensate for dispersion. This is an example of a question here. For wavelength in visible spectrum, the index of refraction for crown glass can be approximated by the relation given by this one here. Question 1 is to find the index of reflection of the glass for light of 400, that is the violet range, 500, that's the mid-range, and 700, that's the red end. Substituting the values in, where lambda should be in nanometers, you'll find that at 400 nanometers is 1.5557, at 700 meters is 1.5353. So it drops as the wavelength increases. Then next, find the phase velocity and group velocity for a pulse with frequency components centered around 500 nanometers. Well, we have that equation. Now here we have a variation of d and d lambda. D and d lambda, you differentiate this and you will get -2 multiplied by this constant divided by lambda to the power of 3. So using that expression that relate Vg to Vp with dispersion, d and d lambda factor inside there. Let's try for 500 because that's what we were asked. This term here is substituted by this, put in the values. Then you find that Vg is about 1.893 times 10 to the power 8 meters per second. So this is definitely less than C. All right, we've come to the end of the lecture. So the learning outcomes for lecture 10, you would be able to derive the resultant superposition of waves that generate beats. You'll be able to differentiate between carrier wave and the envelope wave, which is the modulating part. You should be able to explain group velocity and phase velocity and be able to relate between them. And you should be able to explain normal and anomalous dispersion and when they occur. You should be able to define the situations when we get Vg less than Vp, Vg more than Vp, and also when Vg equals to Vp. And this would be deriving the relation in terms of n and lambda, n and k, n and omega. Thank you for watching.